Hi everyone. I'm just gonna give it a minute after, wait for everyone to come in, and we'll get started here. All right, well, while we're waiting for more people to join, I'll get started with some housekeeping here. Thank you everyone for joining today. As you know, our presentation is being recorded. We will distribute the recording and the slides at the end of the week, and all recordings and slides in the past are available on our website in the archive section. If you have any questions, please raise your hand or drop them in the chat. We can get to questions at the Q&A section in the second half of the meeting, towards the end. Um, with that, I think then we got more people coming in. I will pass it on to Crystal to kick off the presentation.
Hi, everyone. My name is Crystal Molion. I'm one of the engineering managers over at Linkous. Linkous is a sub to ICF on the Gas Emerging Technology program that's administered by SoCalGas. The project I'm going to be talking to you today is called the Multifamily Domestic Hot Water Greenhouse Gas and Cost Project. So that's a really long name. What that means is that we modeled different domestic hot water systems, and then we looked at what their greenhouse gas emissions were and what their operating costs were, and we compared them with a heat pump, water heater, gas, and electric. So I'll get into it. So the team on this project includes myself, the engineering manager. Stephen Long is the director of engineering at ICF, and he provides overall project oversight and looks at all of our deliverables. And Nicholas Fetty and Nicholas Campbell are people on my team that are project managers that helped guide and direct this work and provide a lot of the guidance to the younger engineers. On the agenda for today is an introduction to this project along with background information and then the objectives. Next, I'll present the tariff and emissions used in the study and then how those were used along with a model, Energy Plus model, to determine marginal emissions and operating fuel costs for each system. And lastly, I'll present the total system benefit or TSB analysis for the systems and simple payback analysis along with conclusions. In this project, we evaluated the performance of various domestic hot water systems used in multifamily buildings across California. We started with a baseline system that was an 84% efficient gas-fired boiler with a storage tank. From there, we compared it to a more efficient condensing boiler with a storage tank, then to an electric heat pump water heater, and then to two different configurations of gas absorption heat pumps. In one GAHP configuration, only the city water is preheated by the GAHP, and in the other, both the city water and recirculated water are preheated. In California's climate, GAHPs offer a compelling alternative to condensing boilers and electric heat pumps due to their long-term operating costs and their environmental impacts. So just to give you some background, this slide summarizes findings from two previous gas emerging tech studies that shaped the direction of this project. First, the dual fuel single family modeling study showed that electric heat pumps can cost up to 144% more to operate than gas furnaces in a space heating scenario, depending on the climate zone. This begged the question whether the same thing would be true for electric heat pump water heaters versus gas boilers. In multifamily buildings, higher operating costs are often passed on to renters, many of whom are already cost burdened, so we wanted to investigate the costs. The second study focused on GAHP sizing and design, and in the process of investigating design requirements for gas heat pumps, we also found that electric heat pump water heater retrofits typically require large storage tanks, which many existing mechanical rooms cannot accommodate, which can lead to costly roof installations. And additionally, we anecdotally know that there are multifamily sites which are constrained by the electric panel capacity. And even if they had the space for large tanks, they would require expensive panel upgrades to install the electric heat pump water heater. So these insights from these past studies and anecdotal evidence highlight the need to evaluate alternatives like gas absorption heat pumps for economic feasibility. So these are the core objectives of our assessment. We compared 5 domestic hot water system configurations, starting with a baseline 84% efficient gas boiler and 4 alternatives, which were number 1, a condensing boiler, number 2, an electric heat pump water heater, and then 3 and 4 were the gas absorption heat pump setups. Our analysis focused on utility and capital costs, return on investment, greenhouse gas emissions, and total system benefit. For anyone not from California, total system benefit is a way of calculating the dollar benefit for energy efficiency upgrades. And it's very complex that I don't want to get into, but that's what it essentially is for. And it's something that's used in our programs. All the systems were modeled using deer-based multifamily building prototypes to ensure consistency and relevance across California climate zones. So first, I'm going to talk about how we decided on tariffs and emissions factors to use for the analysis. This slide is showing how we mapped California's climate zones to their corresponding investor-owned utility or IOU in that climate zone to estimate operating costs and greenhouse gas emissions. Each climate zone is assigned to one electric and one gas utility based on the predominant provider in that region. So if there's 2 electric providers in a region, we use the predominant provider. This simplifies the analysis by using a single representative tariff per climate zone. In our tool, we have options for tiered and time of use rate structures to reflect common billing scenarios for multifamily buildings. This table shows how each climate zone aligns with its electric and gas utility, as well as the IOU balancing area, which is either NP15 or SP15, and that affects which emission factors are used in modeling. And this is foundational to calculating the energy costs and emissions across the 16 climate zones. This slide shows the representative electric rate tariffs used in our analysis for each IOU, PG&E, SCE, and SDG&E. For each one, we selected a tiered and a time of use rate plan. These tariffs were chosen based on their multifamily eligibility and broad applicability. We excluded any plans with special qualifiers like electric vehicles, solar, or employee discounts to ensure that the results reflect typical multifamily scenarios. And this table shows the specific tariffs that were used for each IOU, which were applied across the climate zones to calculate energy costs and emissions. This is showing how we calculated the energy costs and emissions for each domestic hot water system. So we accounted for all fixed charges in the rate tariffs and considered how the climate zone, the season, and the baseline allowances influence costs in each hour. The Energy Plus models provided detailed energy use for the entire building and also for the domestic hot water system by itself. To streamline the analysis, we used a custom Excel tool by entering hourly energy data, climate zone, service type, and start year. That tool generates monthly breakdowns of energy consumption, fuel cost, and emissions. So that's a sample output from the tool. This is monthly electricity cost using PG&E's ES multifamily service tariff. We put the outputs from a Deere multifamily model into the tool to give us this table. Each month's usage in this example exceeded the baseline energy consumption tier, placing it in the system in tier 2, which results in higher marginal electricity rates ranging from 43 cents to 45 cents per kilowatt hour. Marginal rates are critical for estimating operating costs of electric systems like electric heat pump water heaters and comparing them to gas-based alternatives. And again, this is based on a default Deere multifamily Energy Plus model with 24 dwellings, each are submetered. And in this table, we use the results from Climate Zone 1, and we tested our workbook across other zones using the same profiles. And the workbook automatically applies the correct tariff based on the selected climate zone and service type, ensuring consistent and accurate cost calculations. This slide is showing the representative gas tariffs used in the analysis. We applied the same selection criteria as we did for the electric tariffs. So we focused on rates that are broadly applicable to multifamily buildings and avoided special programs or qualifiers. Unlike electricity, there are much fewer gas rate options available, which simplified the selection process. This table is showing the chosen tariffs for each IOU. PG&E offers standard residential and multifamily service rates. SoCalGas and SDG&E each provide multifamily and master meter multifamily service rates, and these were used to estimate our gas costs. So running through the same example again with a gas rate, you can see the results. The gas was below the tier in the first 3 months of the year and the last 2 months of the year, and it was in excess for the middle months of the year. This slide is showing how we calculated the greenhouse gas emissions for the domestic hot water systems. We used source, fuel, and emissions factors from the 2024 avoided cost calculator for electricity and natural gas. The ACC provides standardized values for evaluating emissions across different climate zones and different time periods. This table is showing monthly data for a sample model. I forgot to change the name, the AC gas furnace model. It's the same one that we've been looking at for the multifamily. It includes the system and facility energy usage in kilowatt hour and therms and the corresponding greenhouse gas emissions. Note that in this example, the system used only gas, so there was no kilowatt hour usage listed. And the emissions are calculated based on therms consumed with system level and whole facility values provided. So this helps us understand the environmental impact of each system so that we can compare them across regions. So now I'm going to move on to the modeling of the systems in Energy Plus and the analysis of emissions and fuel costs. This slide is showing the Energy Plus translated architecture for the baseline and measure case number 1 systems. The modeling is based on Deere multifamily Energy Plus prototypes, which are widely used for energy efficiency analysis in California. However, the original Deere models did not include a domestic hot water recirculation loop, which is a critical feature in multifamily buildings. So for this study, the modeling team had to modify the Deere prototype to incorporate a primary domestic hot water loop and a recirculation loop. so that we could get more realistic simulations of the system performance. Both systems include a storage tank with a temperature set point of 135 degrees, and the boiler capacity is auto-sized by Energy Plus. The recirculation loop includes non-adiabatic piping to simulate heat loss, and a load profile object schedules flow independently from the demand. Unlike measure cases 2, 3, and 4, which were the heat pumps, this configuration didn't require any heat exchangers between the heat pump water and the potable water, and so the model is able to model the flow dynamics without any needed simplification. This slide is showing the Energy Plus translated architecture for measure case 2, which models a split system electric heat pump water heater with a swing tank. The system includes a storage tank with electric resistance backup to model the swing tank, and it activates if the water temperature drops below the set point of 135 with a 3.6 degree deadband. Just like in the baseline and measure case number 1, both city and recirculation water flow into this tank, which is heated by the electric heat pump water heater. The EcoSizer tool was used to determine the appropriate tank volume and heating capacity for the system. A custom capacity versus storage tank volume curve was developed based on EcoSizer outputs and hard-coded into the model to determine the capacity and storage tank volume needed for each climate zone. One modeling challenge we had here was that Energy Plus does not appear to support a separate swing tank object because it requires every loop to be fully connected and balanced in terms of flow. I have a slide about that later if that doesn't make sense. So introducing a swing tank as a separate object would have required complex flow routing between multiple loops, which Energy Plus couldn't dynamically resolve. So to address this, that's why we combined the swing tank and the storage tank into one with an electric resistance element. This slide shows the Energy Plus translated architecture for measure case 3, which models a GHP working in tandem with a boiler to heat both the city water and the recirculation water. In this configuration, the GAHP and the boiler operate in parallel to heat the storage tank. Energy Plus uses something called a load distribution scheme that we set to optimal, which ensures that each heating device operates at its most efficient part load ratio. The storage tank outlet temperature set point is maintained at 135 degrees, consistent with the other measure cases. The GHP used in this model has a capacity of 123 kBTU per hour, and the boiler and storage tank capacities were auto-sized in the baseline, and they were reused here. This architecture allows the GHP to preheat the mixed recirculation and city water. Modeling this setup in Energy Plus required some simplification. Heat exchangers between the GAHP and the potable water were omitted to avoid overriding flow dynamics in Energy Plus because it can't balance them across parallel branches, as I mentioned earlier. This slide shows the Energy Plus architecture for measure case 4, where the gas absorption heat pump is used to preheat city water only, while the boiler handles recirculation water. This configuration is simplified because the recirculation branch is removed from the right loop, and instead the calculated recirculation energy use is added to the boiler's load on the left loop. This is showing that the GAHP is only preheating incoming cold city water, and the boiler is solely responsible for reheating the recirculated water. The GAHP and the boiler are still operating in parallel with respect to the storage tank, and the load distribution scheme is still set to optimal in Energy Plus. Again, the storage tank outlet temperature is set at 135 degrees. This approach reflects a common industry configuration where the recirculation is handled by the boiler and the city water is preheated by the GAHP. So this is giving an example of the issues that we ran into trying to model heat exchangers or trying to model the swing tank object. This was for the baseline and measure case one system, something that we tried. Initially, we attempted to incorporate heat exchangers to accurately represent the mixing of recirculation water with storage tank water and the blending of those two with the boiler heated water. However, what we found is that heat exchangers behave as active components, which means they override flow dynamics rather than passively transfer heat. We tried using energy management system controls, but we were unable to balance the flow rates on both sides of the heat exchangers, which led to unstable and unrealistic simulation behavior. And as a result, we had to remove the heat exchangers and simplify the architectures to maintain the model stability and ensure we were getting results that were making sense. This limitation underscores the need for improved flow control capabilities in Energy Plus when complex domestic hot water systems are modeled, which have interacting loops. So now we're going to move on to the results. This slide presents a comparison of annual energy consumption across all 16 California climate zones for the baseline and the 4 measure cases. The y-axis shows the total energy consumption in MBTU, and each climate zone is represented along the x-axis. Each group of bars shows 5 cases. The base case is the 84% efficient boiler. Then there is the 97% efficient condensing boiler. Then the electric heat pump water heater. Next, the GHP version 1, which is preheating city and recirculation water. And last, GHP version 2, preheating only the city water. So as we would expect, the base case consistently shows the highest energy use across all the climate zones. The electric heat pump case shows the lowest site energy consumption thanks to its high coefficient of performance, which was 3.2 in our model. The GHP version 1 performs better than version 2 because it's preheating the makeup and the recirculation water, leading to greater energy savings. The condensing boiler shows modest improvements over the base case, but it's not as significant as the heat pump-based systems. This slide shows the annual greenhouse gas emissions for each system across all the 16 climate zones, measured in kilograms of CO2 equivalent. So we have the 5 lines. Again, the boiler at 84% efficiency is in yellow. The boiler at 97% efficiency is in green. The GHP reheating the recirculation is in blue. The GHP not reheating recirculation is in black. And the electric heat pump water heater is in light blue. The boiler with an 84% efficient, or the baseline with an 84% efficient boiler shows the highest emissions, while the electric heat pump water heater and the GHP show significant reductions. In most of the climate zones, the electric heat pump water heater has the lowest emissions, especially in the zones that have cleaner grid electricity. In a couple of the colder zones, the GHP without recirculation sometimes outperforms the electric heat pump water heater in emissions due to just kind of the hourly emissions factors in those climate zones. We also wanted to look at emissions as time goes on. So this slide is showing the projected annual greenhouse gas emissions for the electric heat pump water heater from 2025 to 2034, again measured in kilograms of CO2. You can see that the emissions trend is going down, starting at around 31,200 kilograms in 2025 and dropping to about 25,500 kilograms by 2034. The data here is based on the 2024 avoided cost calculator, which provides us hourly emissions factors for electricity use through 2054. So these factors reflect the expected decarbonization of California's electric grid as more renewable energy sources are added over time. And because the electric heat pump is powered by electricity, its emissions are going to steadily go down as the grid is greened or decarbonized. This slide is presenting the annual operating cost of the 5 systems measured in US dollars. The boiler at 84% efficiency is yellow. The boiler at 97% efficiency is light green. The GHP with recirculation is in teal. The GHP without recirculation is in dark blue. And then the electric heat pump water heater is in light blue at the top there. The electric heat pump water heater consistently shows the highest operating costs across the climate zones because of California's high electricity rates. In contrast, the GHP systems and condensing boiler offer significantly lower costs compared to the 84% efficiency boiler. The GHP with recirculation is generally the most cost-effective in terms of operating costs. The 97% efficiency boiler shows some modest savings over the baseline boiler, but not as much as the GHP systems. Similarly to the emissions, we wanted to look at the operating costs as time goes on. So this slide is showing the projected annual operating costs for the 5 systems from 2025 to 2034. This is again based on data that comes from the avoided cost calculator. Boiler at 84% efficiency is in yellow, 97% is in green. GHP without recirc is in light blue, which is difficult to see. And the GHP with recirc is in light blue, and without recirc is in dark blue. So they're all kind of at the bottom there. And then the electric heat pump water heater is in the light blue. The electric heat pump water heater is showing the steepest cost increase due to rising electricity costs. In contrast, the gas-based systems remain relatively stable and more cost-effective over time. And again, these projections assume that the rate changes follow the ACC escalation trends. Actual utility rates may not adjust annually. This data highlights the economic advantage of gas systems under the current and forecasted rate structures, and the importance of considering the long-term cost trajectories when selecting domestic hot water technologies. So the last thing that I'll show is the total system benefit, or TSB, and simple payback analysis that we did with all of the results that I just showed you. This slide summarizes the cost assumption for each system. All systems use existing storage tanks since Energy Plus auto-sized them much larger than we expected it to. The condensing boiler costs were based on 2024 RS means data. Electric heat pump water heater costs come from the SWWH 028 measure package. That's for large central heat pump water heaters. That included equipment, labor, and infrastructure. For the GHP systems, the material and labor costs were sourced from field study work that is also being done through the GET program, including actual proposals for GHP units and their installation. Both versions of the GHP are assumed to have identical costs. So this table shows a clear cost difference with GHPs being the most expensive, followed by electric heat pump water heaters and then condensing boilers. This slide shows the total system benefit for each system across the selected climate zones. The TSB accounts for energy savings as well as refrigerant impacts, calculating using the CEDAR's cost effectiveness, or CET, and the refrigerant avoided cost calculator 3.0, that would be RAC. Since the electric heat pump water heater includes some refrigerant costs because it uses refrigerants that have environmental impacts. The GHP uses a refrigerant with zero GWP because it's ammonia, so its refrigerant costs are excluded. As shown in the table, the GHP version 1 and electric heat pump water heater generally offer the highest TSB values, especially in cooler zones. This slide shows the simple payback period to the customer, which is the number of years it takes for each system to recover its installation costs through energy savings alone. The same systems are compared, as you can see. The condensing boiler consistently shows the shortest paybacks, typically under 2 years, because it has a low upfront cost. The electric heat pump water heater does not have payback because its operating costs are higher than they were in the baseline. The GAHP systems show variable payback periods. In cooler zones, like zones 1 through 5, payback is under 7 years. In warmer zones, like 10 through 15, payback exceeds 20 years, which is longer than the EUL or expected useful life of the system. And the cells highlighted in yellow indicate zones where there is no payback or there isn't a payback within the equipment's lifetime, making it financially more difficult to install in those regions. So these are the key findings and economic insights from the study. Firstly, all systems, condensing boilers, electric heat pumps, and gas heat pumps reduced energy use and greenhouse gas emissions compared to the baseline 84% efficient boiler. However, not all of the systems reduced the fuel costs. The electric heat pump water heater had the lowest site energy use, but its operating costs were about 3 times higher than the gas systems, making it the most expensive one to run. The GAHP systems performed well in terms of emissions, especially in cooler climate zones, and in some cases matched or outperformed the electric heat pump water heater. Economically, the condensing boiler had the shortest payback period thanks to its low upfront cost, even though its energy savings were modest. The electric heat pump water heater didn't have a simple payback due to its high operating costs. The GAHPs show strong potential in favorable climate zones with payback periods as short as 4 years, but they weren't as cost-effective in warmer climate zones where energy savings were smaller. So these results highlight again the importance of the climate zone, the fuel type, and the system cost when selecting domestic hot water technologies in multifamily buildings. And lastly are the recommendations. This slide outlines 3 key recommendations based on the study findings. The first is that GAHP systems show a strong balance of efficiency and cost effectiveness, particularly in cooler climate zones. They outperform electric heat pump water heaters in operating costs in most cases and sometimes in emissions. To encourage adoption, we recommend targeted incentives for GAHP installations in favorable regions. Second, we've identified limitations in Energy Plus modeling, especially around recirculation loops and additional objects like swing tanks or heat exchangers. Enhancing simulation capabilities would improve accuracy and support better modeling. Lastly, we recommend further research into the long-term performance and maintenance costs of GAHP systems that will help assess their reliability and inform future program planning for multifamily buildings. Thank you, everyone. I think we have about 15 minutes for any questions. And I'm in presenter mode, so I cannot see hands. So Kate, if you want to call on people, that would be great.
Yep. If anyone has questions, just drop them in the chat and I can unmute you if you raise your hand.
I'll bring one up for the audience. Oh, we got an audience one. Okay, we'll have Mike go first.
All right, Michael, you should be good to unmute yourself and ask your question.
All right, I think I'm unmuted now.
Yeah, we can hear you.
Yeah, thank you for the presentation. Explain a little bit deeper why the gas heat pumps didn't do as well in warm climates. That's kind of exactly the opposite of what I would think the COP should be higher. So what's the physical mechanism in there causing that result?
You mean the simple payback in the warm climates?
Yes.
That's because in warm climates, you don't have as much water heating that's needed. And so your energy savings are less. And because the cost of the system installation is the same, no matter if you're in a cold or a warm zone, the energy savings over cost is just not as good in a warm zone. The performance as far as COP is better in a warm zone.
So it's all tied to the groundwater temperature.
Yeah.
And what was the variation in groundwater temperature between the cold zones and the warm zones?
It's a good question. I don't know off the top of my head. I can email you. The minimum cold water temperature in climate zone 9, which is LA County, is 65 degrees Fahrenheit. In Northern California, I would have to get back to you. I can email you. I'm not sure what it is.
Okay. Thank you.
And then there's another hand. Alejandro, I don't know if you can unmute yourself yet.
All right, should be good to go now.
Yeah, thank you. Maybe I missed part of the details on the presentation, but I was wondering how across these 16 climate zones, how was, what was the exercise in the modeling aspect what pertains with sizing and so on and so forth? Because I will assume, like you mentioned, you have different loads across different climate zones. So I'm imagine that there was some sort of parameter that drove the sizing of the multiple components across the.
Yeah, so let me get back to those. I think it's a little easier to talk through them. So for the baseline and the condensing boiler, Energy Plus auto sizes the boiler capacity and the storage tank volume. The water fixture demand for every climate zone is the same. So we just assume everybody's using the same amount of water, no matter where they are. Same thing for the recirculation load. We just had a constant recirculation load, GPM and heat losses. And so the sizing is really only related to the city to the potable city water temperature that's coming out from the ground. So if it's in a colder climate zone, you're going to have more load because you have to do more heating. And so Energy Plus auto size that for us. I can't speak to how it decides the size. Nick could maybe jump in if he's around and explain that, but that's how the sizing is done for that one. For the electric heat pump, if you go into EcoSizer and you put in certain number of multifamily apartments with a certain temperature set point and number of people per apartment, it gives you a curve that you can adjust the storage tank volume and the electric heat pump capacity. And so we put that kind of storage tank versus capacity into Energy Plus, and then we again let it size the storage tank and the electric heat pump capacity for us. And we're using the same flow rates and the same recirculation load as we were before. So again, it's really just the difference in groundwater temperature. And then for the GAHP, the boiler and the water heater storage tank are going to be already auto-sized from the baseline model. And we are simply adding an additional capacity of the GAHP. So in this case, we were using the 123 kBTU GAHP. And the reason that we decided to do that instead of having auto-sizing going on is because Generally, in a retrofit situation, you're going to leave the boiler and the storage tank there, and you're going to add a GHP onto the system. So we thought that that was the most realistic modeling scenario.
I guess, yeah, I don't know how much the sensitivity analysis was done in terms of set points, if whether the recirc was attached to the GHP or not. But yeah, this is helpful. Thank you.
Yeah, no problem. We didn't have scope to do a sensitivity analysis. But your point is taken that there could be sensitivity depending on whether you have a higher heat rate capacity in the boiler or higher water storage tank volume, excuse me. But speaking to whether you're reheating the recirc or not, that's the difference between measure case 3 here, where you are reheating the recirc, and measure case 4, where you're not reheating the recirc. So I wouldn't call it sensitivity, but those are different results that we presented.
Just last, just so I understand, what was your peak GHP and your daily utilization, and what was your recirc load, so I can reference these results with it?
I do not know off the top of my head. Is that something you could email me to ask, and I can get back to you?
Awesome, sounds good. Thank you.
Crystal, you've got 2 questions in the chat. First one's from Paul Kylo. Given that GHAPs perform better than electric heat pumps in several climate zones, what is the primary challenge to achieve greater adoption of the technology?
There's a few challenges. One is that customers are just not aware of the technology. The second is, like electric heat pump water heaters, these require some different sizing practices than typical boilers. And we haven't had a lot of support from one of the manufacturers on sizing and getting diagrams that can be submitted to plan check. The other manufacturer is really great and provides all that stuff for you. So that's another challenge. And then I would say the third challenge is really kind of, in some people's mind, I would call it an anti-gas bias, just not wanting to use gas, even though the GAHPs do save emissions and they are cheaper to run. There's a perception that electric heat pump water heaters are the best thing that you could possibly do. So that's probably number 3.
I'll throw in one other that's not part of the study, but in general, you can correct me if I'm wrong, but I think the contracting design community also is maybe challenged with these.
Yeah, I would say that's true. And that goes back to providing support for the design. The MEP engineers that put together documents that are submitted to plan check, they really rely heavily on manufacturers to provide them with sizing guidance and to check their work. They kind of check each other's work. So when a manufacturer doesn't provide that kind of assistance, then it becomes really difficult for the engineer to take the risk because it's their stamp on the diagram. And if something happens, their insurance is going to get hit if somebody runs out of hot water or something breaks. Another issue is for new construction. I've been talking about retrofit here, but specifically for new construction. I don't work in that space, but when I speak to people at conferences, it seems like new construction really doesn't favor any kind of gas incentives. I don't know if that's true if you looked in the nitty-gritty details, but that's kind of the overall thing that I hear. And then we had another question.
There was another question from Ryan Rodriguez. Says, apologies if I missed it, but how were heat exchanger inefficiencies losses accounted for since they are not able to be modeled in Energy Plus?
That's a good question. I don't know that we were able to address that. Again, we had a simplified architecture here because there was a lot of issues when we did try to model the heat exchangers. like I showed here. This is one example where we tried to put a heat exchanger. We also tried to put a heat exchanger between the GHP and the boiler system, and that would have resulted in 3 loops here, and that just did not work. So I don't know that we addressed the heat exchanger inefficiencies, to be honest with you. Anything else?
Oh, one more popped in. Michael Garabrandt, given this as a retrofit analysis, was the marginal grid emissions factor used?
Yes.
And Ryan just responded, thank you, great presentation, very informative.
Oh, thank you. All right. I will be sending the slides over to Kate, who will be posting them if you guys want to look at them a little bit more closely. If you have
There's
any
a few
more.
questions.
Oh, there
Yeah.
are. I'm sorry. Again, I'm
Two
in
more.
remote. I can't see anything.
No, you're good. From Alejandro, what was the EHPWH used? And then Melissa, really quick, yes, the slides will be shared. I'll be sending those over by the end of the week.
What was the electric heat pump water heater used? Do you mean what was the COP or what kind? We used a split system with a swing tank, if that was the question, and the COP was 3.2.
I was referring more to, is this a CO2 heat pump, so high delta T, or do you use a R134A or more like the latest 513 systems?
The performance
Which can
curve we
hand-
used was for R134A.
Oh, okay. So your system, yeah. So you were cutting off the system at ambient temperatures that were lower than 35, right?
Yes, but I don't believe we had any that were much lower than that, even in our higher Northern California climate zones.
Yeah,
I don't know that we
actually
cut it
I do
off,
forget about
but
that
we
one.
don't have a lot that
Good
are that
point.
low.
And then one more question from Michael. Okay, how sensitive were the payback and other ROI issues to electric and gas rates? And was there any effort to model how the ROI metrics would change based on forecasted changes in the electric/gas rates?
Okay, there was a lot to that. As far as how sensitive they are, off the top of my head, I don't know. Email me and I'll get back to you. We did not try to forecast how ROIs change with electric rate or gas rate changes. But it's a good idea.
And I'll drop Crystal's email in the chat just so everyone can have it.
Yeah, these are really great questions. Definitely, we could refine this analysis a lot more with this input. This was the first time we were using the GHP Energy Plus object. So we ran into a lot of interesting things. And some of the things that we would have loved to investigate, we didn't have the time to do after we kind of resolved some of these modeling issues and created some workarounds.
Any other questions, either online or chat? Well, Crystal, thank you for the great presentation, and for those of you who attended, thank you for showing up. And you've got Crystal's email if you've got further questions.
Yeah, feel free to email me. Thanks for all the questions. Appreciate it. It's always great when people want to know more about what you did. So if you think of anything else, feel free to reach out.
Perfect. Thank you so much, everyone.
All right. Bye-bye.